Hello my dear friends, welcome back to our YouTube channel. This is ADC Maths. Cayley-Hamilton theorem. How to verify the theorem and what are the uses of the Cayley-Hamilton theorem? Let us see in this video. First of all, what is the statement of the Cayley-Hamilton theorem? Every square matrix satisfies its own characteristic equation. So how we will get the characteristic equation? From the matrix only, isn't it? So once we replace the lambda value in the characteristic equation by the matrix, given matrix A, then automatically it satisfies the characteristic equation. Left hand side is equal to right hand side. So this is the verification of the Cayley-Hamilton theorem. And apart from that, as you know that, what is the real application? What is the use of the Cayley-Hamilton theorem? With the minimum computations, with the minimum calculations, we can find out the powers of the matrix as well as the inverse of the matrix. Not only the powers and inverse, and also let us simplify the given matrix expression with the minimum computation works. That's very, very important. So that is the real application of the Cayley-Hamilton theorem. So let us coming back to this question now. So verify the Cayley-Hamilton theorem for the 2 by 2 matrix A equal to 1, 2, 4, 3. So first of all, find out the characteristic equation. So as we know that the characteristic equation of A is, the characteristic equation of the given matrix A is determinant of A minus lambda I is equal to 0. So this is the 2 by 2 matrix. So there is lambda squared minus S1 lambda plus S2 is equal to 0. Where, what about the S1? S1 is the sum of the leading diagonal elements, or is often called as the trace of the matrix, right? So 1 plus 3 is equal to 4. What about S2? S2 is the determinant of the matrix, the determinant of 1, 2, 4, 3. So this is equal to 3 1s are 3 minus 4 2s are 8 is equal to minus 5. If I substitute the S1, S2 in this characteristic equation, we get lambda squared minus 4 lambda minus 5 is equal to 0. Is that right? Is that right? It's clear? Normally, when we solve this characteristic equation, we will get the corresponding eigenvalues as well as the eigenvectors. But this time, that is not the question. The question is verify the Cayley-Hamilton theorem. So what is the statement? It says that every square matrix satisfies its own characteristic equation. So that means that if I replace lambda by the given matrix A, we get what we get. Substitute lambda is equal to A, we get A squared minus 4A minus 5 into I. What is I? I is the identity matrix of 2 by 2 order. That is of same order of A. What's the A? A is of 2 by 2 matrix. So I is also 2 by 2 matrix, identity matrix, or is called a unit matrix. What is a unit matrix? 1 0 0 1. Is that sir? Is equal to 0 matrix. This is called the 0 matrix. So this is the equation. I would like to verify this. I would like to verify this star equation. A squared minus 4A minus 5I is equal to 0 matrix. So what is the verification? So the verification, what is the verification says that I need to verify that left hand side A squared minus 4A minus 5I is equal to 0 matrix is equal to right hand side. So I want to verify this one. So now find out the A squared first. Now find out the A squared. A squared is equal to A into A. So A is 1 2 4 3 and into 1 2 4 3. So as we know the matrix multiplication, this into this. Is right sir? So 1 1s are 1, okay, 1 into 1, 1 plus 4 into 8 is 9, that's it. 1 2s are 2 and plus 2 3s are 6, so it is 8, and 4 1s are 4 plus 3 4s are 12, so it is 16, 4 2s are 8 plus 9 it is 17, so it is A squared value. Now I like to verify the theorem. So what's the left hand side here? A squared minus 4A minus 5I. Now I know the A square value, it is 9, 8, 16, 17. Minus 4 into A. A is a given matrix 1, 2, 4, 3. minus 5 into, what is I? I is the identity matrix. Now the A is 2 by 2, so I is also 2 by 2. Let us simplify this. We get this 9, 8, 16, 17, right? And this is 4, 8, 16, 12. And mine is 5, 0, 0, 5. So what does it mean that? This means that 9 minus 4 minus 5. 8 minus 8 minus 0. And 16 minus 16 minus 0. And 17 minus 12 minus 5. As you see that 0, 0, 0, 0 is equal to 0 matrix. So that is the right hand side. Hence, the theorem is verified. Hence, the Cayley-Hamilton theorem is verified. So once the theorem is verified, with the help of this star equation, I would like to find out the a power 3 and a power minus 1. Already we know what is a cube. A cube is, what is a cube? A cube is nothing but a squared into a, isn't it? Already we know the a squared, so once again multiply by the a, we get the answer. But this time, I don't go by the usual product. I would like to use the Cayley-Hamilton theorem. So from this Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. That means that a squared minus 4a minus 5i equal to 0. So this is the given star equation. So can we use the star equation? We'll get the a cube as well as a power minus 1. How? Let us see that. How to get the a power 3 now. So to find the a power 3 first, to find the a to the power 3, just how to get the a power 3 from the star equation? Pre-multiplying, because the star equation a squared is maximum. So pre-multiplying a on both sides of the star equations. Both sides of the star equation, we get a into pre-multiplying means before a squared minus 4a minus 5i is equal to a into 0 matrix is equal to 0 matrix. So let's multiply a into the term, we get this a cube minus a into a, 4a squared, a into I. What's the a into I? A into I is equal to a. Is right? So minus 5, a is equal to 0 matrix. My question is a cube. So let's fix the a cube in the left hand side. Others can be pushed into the right hand side. So 4a squared minus 5a. Now already we know the a squared value. It is 9, 8, 16, 17. Now minus 5 into a is a given one, 1, 2, 4, 3. So let us simplify this, we get the answer. What is this? 4 9s are 36. 36 minus 5, 31. So 31 is the answer. Then 42 is. 41 is the answer. 41. Then 4 is a 32. 32 minus 10. It is 32 minus 10. How much? It is 4a squared. 32 minus 10. How much? A cube is equal to 4a squared. A squared is 9, 8, 16, 7, 17 minus 5 into 1, 2, 4, 3. So 4 3s are 36 minus 36. I think so. This is plus 1, you know. Yes, right? Because minus or minus plus. So 36 plus 1, 41, right? Then it is 8 4s are 32. 32 plus 10, 42. 4 into 16, 64. 64 plus 20. 64 plus 20, 84. Then finally, it is the 4 into 17 plus 15 is 83. So this is the 83. So we get the a cube with the minimum computation, with the minimum calculation. So this is the one of the application of the Cayley-Hamilton theorem. Then what about the a power minus 1? So how to get the a power minus 1? Let us see that. How to get the a power minus 1? The same idea. Pre-multiplying a power minus 1 in the star equation. Pre-multiplying the a power minus 1 in the star equation, you will get the a power minus 1. So can I multiply the a power minus 1 in the star equation? Pre-multiplying. So to find a power minus 1, once again pre-multiplying a inverse on both sides of star. Both sides of star we get. So the star equation is already there in the blackboard. A squared minus 4a minus 5i is equal to a inverse into 0 matrix is equal to 0 matrix. Now multiplying a power minus 1 to a square is a. A power minus 1 to a, yeah, because a power minus 1 into a squared is a power minus 1 plus 2 is equal to a power 1. What is a power minus 1 into a? It is I. What is a power minus 1 into I? Is equal to a inverse. So let us multiply into the term a inverse into a is I. So 4i, a inverse into I is I. A inverse is equal to 0 matrix. So let us fix the inverse term to the next side. So 5a inverse is equal to a minus 4i. So by that way, a inverse is equal to 1 by 5 into, what is the a? 1, 2, 4, 3. What about the 4i? 4 into 1, 0, 0, 1. That's right? 1, 0, 0, 1. So after that, this is 1 by 5, 1, 2, 4, 3 minus 4, 0, 0, 4. So let us subtract. We get 1 by 5 into 1 minus 4 minus 3, 2 minus 0, 2, 4 minus 0, 4, 3 minus 4 minus 1. So this is the A inverse. So usually when we find out the inverse of the matrix, I need to get the adjoint of A. But 2 by 2 matrix, so I don't use that olden techniques, that is the adjoint of A technique. And what's the formula for A inverse in the technique? That is the olden technique. It is 1 by determinant of A to adjoint of A. So adjoint of A I never used here. But determinant of A, yes, what's determinant of A is nothing but the determinant of the matrix, it is nothing but 3 minus 8 is 5, so there is 5 is there. The same thing here, this indicates the determinant of the matrix, right? So this is the the application of the use of the Cayley-Hamilton theorem. I am using here for the 2 by 2 matrices, 2 by 2 matrix, and one more technique is to solve or to find or to evaluate the given very lengthy matrix expression with the help of Cayley-Hamilton theorem, which makes very simple without any the major and very lengthy computational works. So with the minimum computational works, we can find out the given powers of A as well as the inverse of A as well as the matrix expression. So this is the real use of the Cayley-Hamilton theorem. Thank you so much for watching our YouTube channel. Please kindly subscribe and comment, share to your friends our ADC Max YouTube channel. Thank you so much.